Welcome back, everyone. Hope y'all had a good reading week, and hope you're happy that the temperatures are finally above freezing. I feel like that's a miracle. So we left off last week talking about hash tables, and we're going to spend the first bit of this week continuing to talk about them. Just as a little review, a hash table is commonly used to implement an ADT called a table. And that's also called dictionary sometimes. In Python, it's definitely called a dictionary. And it's a collection of entries that consist of unique keys plus additional data. So some sort of mapping from keys to data. A hash table stores entries in an array and chooses array indices according to a hash function. Going to finish this review, and then, as I just remembered, I was going to talk about the next assignment. So, like I said, I'll do that after this review is done. A hash function works in two parts. They're interchangeable, actually. A hash code takes non-integer keys and converts them into integers. So, if your keys are numbers, this is unnecessary, or assuming they're integers. But if you're mapping things like names to data associated with that name, then you'll need to have a way to take the non-integer keys and turn them into integers that can be used as array indices. And then the compression map takes the hash code, which may or may not be a valid array index, and then map it into the range 0 to n-1 in order to fit the array. A good hash function should be fast to compute and minimize collisions. And this week we're going to talk about how to achieve both of those things. But before we get into that, you may have noticed that there's a new assignment. This one's almost all code. Like I've been saying throughout the course, the beginning was very abstract, and now we're actually talking about data structures. From a high level, the goal of the assignment is to sort of drill in the idea of interface versus implementation, abstract data type versus data structure, by implementing an ADT using two different data structures. You have a class of things that you want to store, in this case fish, which are associated with their keys being their species name. And using that, that class of data items that you want to store, you make a ADT or data structure to store them. This is also an example of how there isn't a specific list of all of the ADTs. You can just make up an ADT. And that's what I did for this assignment. This ADT has a lot in common with a table, but it's not quite the same because the specification of table that we're using in class doesn't have things like clone and duplicate. Pretty important is that in this assignment, you're not really writing any programs. You're just writing a part of a program that would hypothetically be inserted into another program. And that could very quickly spell disaster for correctness of code because you have no way to test it. So I wrote up some tests for the ADT. The file is on UMLearn alongside the assignment. And I'll show off like what it should look like when ran. So if you just run it like this, you'll get a little error message. Assertions need to be enabled for the test to work. So if that happens, just follow the instructions. You need to tell it to enable assertions. And then you get some happier output. The assertions in question are lines like these. This isn't really what unit tests look like in the real world, but I chose to do this because it's basically the simplest possible way to do tests. I wanted to make sure that it worked without installing any additional frameworks or anything like that. You can certainly write additional tests if you want, but I think that mine should be thorough enough. Question 3 is the exact same as question 2, except instead of using a linked list, it uses a hash table. I think you can do questions 0 through 2 right now if you really wanted to, but question 3 requires some of the stuff we'll learn about this week. I guess you could do this one too immediately because the lecture slides are online, but if you're just following along with the lectures themselves, you'll need this week's content to do question 3. So you got to use a polynomial hash function. What's that? Horner's method, and separate chaining. Very strange. Wonder what those terms mean. And yeah, the instructions for that one are real short because it's just do all this again. Finally, the written question looks into a pretty neat technique for estimating the number of instances of a certain object in a very large data set. Like the fish inventory ADT that the other questions are about, lets you tell exactly how many fish of a given type are in your inventory. But say like you have an absolutely massive amount of them, like millions or billions. You can't fit all that in memory. So you could actually use hash tables to store the data such that you could get pretty good estimates of the number of instances of a given object, like say how many fish of a certain type are in your inventory. It gives you pretty good estimates, not always completely accurate, but while saving you quite a bit of space. So you get a definition, an example, and then I grill you on it. It's like a really long quiz. So that's all for the overview of this assignment. Any questions about it? Well, if you do, put your hand up during the lecture, talk to me after class, email me, whatever. Discussion forums are open, the usual. Let's get back to the lecture. We're going to talk about hash codes first. If your hash code, if the key associated with the data you're inserting into a hash table is an integer, then the hash code is trivial. Just literally return the integer that you're given. And then, like I mentioned before, non-integer keys, such as strings, are a bit more complicated. But the next level of complexity isn't that much worse than just directly working with integers. If your key isn't an integer but is like roughly the same size as an integer in memory, no larger, then you can just cast it to an integer. Each character in a string uses the same amount of memory as an integer, so you could just cast that character directly into an integer. More complicated than that is a string, and also much more common than using single characters. You can use the fact that each character is castable to an integer to start with. If we have the key cat, then we can start by mapping C to 3, A to 1, T to 20. But then we just have a list of numbers, whereas we want 1. And there are some different strategies, some of which are better than others, that we could use to get that single number. Our first idea is to add up the integers. So cat would be 20 plus 1 plus 3, which is 24. But that runs into a problem that is basically one of the things that we want to always avoid with these functions. There's a pattern in the hash codes, and that's that any strings that consist of the same characters as cat will also get that key 24. More generally, patterns in the keys give rise to patterns in the indices, and that's very bad. Data in the real world often follows patterns, and we don't want those to translate to patterns in our indices because that causes collisions, and that's very bad. So this is a new strategy. This is actually the polynomial hash code described or mentioned in the assignment. And that is basically using the letters, or the integers corresponding to the letters, as coefficients in a polynomial, and evaluating that polynomial at a specific value of x or n or whatever. The whole reason why we do that, because it's definitely not immediately obvious why a polynomial does better than just a regular old adding function. It weighs the different letters differently. The first letter contributes more to that final hash code than the ones after it. And that makes it so anagrams, different arrangements of the same letters, don't end up with the same hash code. So if we have act, that would previously have the same hash code as cat, but now you can see that they're quite different. So again, in general, we want to avoid patterns in the hash map. The perfect hash function is one that uniformly distributes its array indices across the array. Discussions about data structures and algorithms and most implementation details in the real world will have sort of back and forth like this. We have a problem, we have a crappy solution, we find a better solution, but then it has some drawbacks, pros and cons and pros and cons. And you have to find the best trade-offs for your situation. So that polynomial hash code does have the advantage over just adding up the letters' values because it gives you a better distribution of indices, but it has some drawbacks. The results can be very large. If you have a long word that you're hashing, then those exponents will get really big. And also, calculating all these terms can be time consuming. Since you're doing an operation for each letter of the string, it's like at least linear time, but as you'll see very soon, it's actually worse than that. I won't make you guys do this. The answer's right after this. But we want to analyze, for our polynomial hash code, how many addition and multiplication operations are required to calculate it. And you're supposed to write the answer in big O notation, and I want to highlight that this is an example of another widespread use of big O notation. So far, we've just been using it to count steps that a program takes, like any amount or constant amount of operations. But sometimes certain operations take much more time than others. A really good example is network access. If you're writing code that connects to the internet, sending for data across the network and waiting to hear back from other devices takes so much longer than everything else that all of the code that runs locally on your machine may as well take zero time. And then if you're calculating the time complexity of an algorithm, you would only count network accesses. In a similar vein, we only care about how many addition and multiplication operations are in this algorithm, and we'll pretty soon see that addition is kind of insignificant too. Spoiler alert, it's quadratic time. But for each a to the power of j, it takes j minus 1 multiplication operations. That's because this block of code is what we do for each term of the polynomial. And we see that it's a for loop, I equals 1 less than j. That's j minus 1 iterations. That was all the cleverness required, I think. The rest is summation manipulation. And then once you have all of your exponents calculated, like all of those terms given a specific value, you also need m additions, so one for each term, just to add them all together. But that doesn't really matter for our calculation for two reasons. One is to do with asymptotic notation. We've seen in lots of examples already how if there's a function with a quadratic term, so like raised to the power of 2, and a term with a linear term, raised to the power of 1, then the quadratic one sort of dominates the linear one, and the result is just O of, in this case, m squared. It's useless to say O of m squared plus m, because m squared grows so much faster than m that we only have to worry about that. The other reason is a bit more practical and like down to the metal of how this actually works, and like it's just that multiplication is repeated addition. Every multiplication operation takes as much time as several addition operations. So that gives you some intuition that maybe multiplication matters a lot more, makes a much larger impact on the time complexity of an algorithm than addition. And you'd be right, and you'd be double right, because there aren't even a large enough amount of addition operations to meaningfully affect the execution time. Quadratic time, usually called O of n squared, but we're using an m, so it's m squared, is not that good. It's the difference between taking 10 steps and taking 100 steps on an operation that acts on 10 things. And like in the real world, do you want to aim for n log n probably, or more often linear time? Quadratic time is kind of unacceptable, and we want to try and make it better. Of course, if you go into theory like me, then you'd look at that and say, oh, that's a polynomial, it's efficient. And if you go even deeper into theory, go into computability theory, Comp 3030, very fun course, I'm going to keep recommending it forever. You'll look at that and go like, oh, it's finite, it's a good algorithm. But we're done with theory. We went through a theory phase earlier this year. This is practical, and O of m squared is bad. Luckily, we can still use the same basic idea, but do some clever algebra to save us some work. You may notice that all these terms, well, most of them, C0 here is a bit lonely, almost all of these terms have an A in them, so we can factor out that A. And then in the brackets, all but one of the terms have an A in them, so you can factor that out. In those brackets, you can probably see where this is going. Factoring out a bunch, it turns out, saves us a lot of work because it's just the distributive property in action. Instead of multiplying A by that, and that, and that, and that, and adding those all together, you can do the addition first. And since multiplication distributes over addition, taking or multiplying the sum by something has the same effect as multiplying that same something by every term in the sum. So when we evaluate that sum, we start out in the innermost set of brackets and then just keep evaluating sort of outwards, keep simplifying it until you're left with only one term. And then each of those terms requires one addition and one multiplication to compute, and the overall calculation has m terms, so that's one addition, one multiplication times m, so that's 2m calculations. You could still argue that the multiplications are more significant than the additions, and thus we should say that it's like m operations plus some insignificant extra amount. But luckily, asymptotic notation does that for us. It's O of n. This is Horner's method. And the exercise to the reader is actually the assignment, or part of it. So I'm going to completely skip over that part. So let's go back to those disadvantages we were complaining about. We just solved the problem of it being fast to compute. Getting the same results while speeding up your algorithm from O of m squared to O of m is a huge improvement. Your boss would look at that and just assign you extra work. Yay. There's still one more drawback, and it's that the results can be very large. You know from the theory section of the course that any polynomial with a slightly higher exponent grows way faster than a polynomial with a slightly lower exponent. And this thing gives you increasingly large exponents based on how long the string is. So just in terms of how fast that array index grows, not the runtime, a string with 10 letters, you could definitely imagine a name having 10 letters in it, would require you to evaluate a polynomial of degree 10, which is probably going to be humongous. So we need some way to make these results a lot smaller. Basically a compression map. The compression map in question is actually one that we've seen before. We can take the answer modulo the array size. And isn't this cool? Modulo has a distributive property in itself, kinda. The left side and the right side of these kinda sorta equations, equivalencies would be a better word. The two sides of these equivalencies aren't exactly the same, but this triple-lined equals symbol means that they're equivalent modulo n, which means that if you divide each side by n, you'll get the same remainder. And then that means that if you mod it by n one more time, then you'll get totally identical answers. Here's an example of that technique. Say you have a really big multiplication operation to do, and you have a reasonable array size. Let's say it's, it must be 10. I think that's too small to be reasonable, but certainly reasonable for an example. The hard way is to just do that multiplication, end up with a number that's way bigger than 10, will cause the biggest array index out of bounds exception you've ever seen, and then take the modulo 10 of it just to get 1. The easier way is to mod each term of the multiplication expression by 10, then you get 3 and 7. Multiply those, and the answer isn't the same as the thing we got earlier, but it's equivalent modulo n, in this case, equivalent modulo 10. Which means that if you mod both these by 10, you'll get the same number. You'll end up with 1 through an easier technique. And also, I'm sure you all already know this, but equivalently, equivalent modulo n, getting the same answer if you take that number mod n, means that they have the same remainder when divided by n. 1 divided by 10 is going to have a remainder of 1. 21 divided by 10 is also going to have a remainder of 1. Consequently, you're going to do this on your assignment. Horner's method is decently fast and gives you good hash values, but you just have to take a modulo n after each step of the calculation, and then that'll keep the array indices actually fitting in your array. Now for a slightly different topic. This one's more interesting, I think. Collision resolution. We've been spending all of our time talking about hash tables just trying to avoid collisions. We want to get hash codes such that things like cat and act don't get the same array index, and just generally different keys get different array indices as much as possible. But we can reduce collisions all we want, but preventing them is impossible. You need to have a strategy in place, or in this case, an algorithm in place, in order to handle collisions when they happen. Oh yeah, before we move on, I should probably read the slides. This is an important point for that compression map that I talked about earlier. So if k, the key, and n, the array length, share a common factor, then h of k will also be divisible by that factor. And then once you do that extra modulo operation, you'll probably end up with the exact same array index for different keys that are divisible by the same factor. So to get around that, you want to choose an n such that there are as few common factors with any given k as possible. And you know what numbers have the fewest common factors with anything? Prime numbers. So because of that little mathematical quirk with modulo, hash tables almost always have a length that is a prime number. Here's the first strategy for addressing collisions. We have a key k, calculate hk, and check index k, h of k in the array. If it's not occupied, cool, there's no collision, we're fine. Just insert the entry there. But then if there is a collision, if that array index already has something in it, then search the positions following it in some pattern, usually just a linear search, and then insert the entry into the first available position that you find. The common way to do this is to just check indices in a linear order, but some slightly weirder methods of doing this can get slightly better results, just owing to the fact that if there are a lot of collisions, then with this strategy, there would be a lot of colliding objects clustered around the same place. As an example of this, say we're making a table of reference books. The hash map is bad, but don't worry about it. Is to take the first letter of the author's last name and convert it to an integer from 0 to 25. And then you insert the following names in this order. A hashes to 0 because the first letter of the author's last name, A, is the first letter in the alphabet, goes there. And then we insert another A name into it. We attempt to insert it into index 0, but there's already something there. So we move one to the side. That index is not occupied, so we put it there. C hashes to 2 because it's the third letter of the alphabet. We put it there, and we're fine. Then B hashes to 1 because it's the second letter. We want to put it in index 1, but there's already something there. There's also already something in index 2, so we put it in index 3. And then if you search for Bredon, the guy whose name starts with B, your hash map will give you an index of 1. So you have to do that same linear probing as before when we inserted Bredon's name into it. Start at index 1, it's not what we want. Index 2, not what we want either. Index 3, that's good. This should maybe remind you of something. This searching algorithm. Oh wait, I totally missed a slide. We're still on this example. But this should remind you of something. I'll get into that after. So suppose you search for a book by Anderson. Anderson has not written any books that are currently in our table. So how many indices do you have to search before you can be sure that the hash table doesn't contain it? Well, the last name starts with A, so it hashes to 0. That's not Anderson. Check the next one. That's not Anderson. That's not Anderson. That's not Anderson. And that's empty. So you have to keep walking forward through the array until you find the thing you're looking for, you find the thing you're looking for, or an empty position, or in the worst case, you've looked through the entire array and you end up back in the thing that you know is in index 0. This definition will help us talk about why open addressing can be bad. The load factor of a hash table is basically just how full it is. Number of entries divided by the size of the array. So if it's half full, then number of entries will be half of the size of the array, and then the load factor will be 1/2. Easy. This strategy is acceptable for tables with low load factors, so lots of empty spaces. But the performance goes from acceptable to catastrophically bad if the table has a load factor of 0.75, 3/4, or more. This isn't something that's been proven in a paper. That's just an empirical result. Some people ran a bunch of experiments and found that the performance tends to get bad when the table is 75% full or more. Now, for that thing that I said the search algorithm should remind you of. In the worst case, searching takes linear time, like linear search, because you have to iterate through most of the entries in the table. So if your hash table is working well, then you can do things in constant time. Like, I want to search for Cushman. Starts with C. That's the third letter of the alphabet, so our index should be 2. Check index 2. It's right there. Cool. Constant time. But if it doesn't work so well, you want to look for Anderson. Hash to 0. It's not there. It's not there. It's not there. It's not there. And now imagine you're storing 1,000 books and you have to take 1,000 steps to address that. No good. So I think that also shows off the importance of trying to prevent collisions in the first place. I remarked earlier that going by the first letter of the author's last name is a bad hash map. And that's because patterns in the patterns in the keys led to patterns in the indices. We could have done or used a much better hash function that puts alfors and auden in like completely different places, and then we'd have our constant time fun that hash tables are made for. So both the method you use for preventing collisions and the method you use for dealing with collisions when they inevitably happen anyway are important. Strategy 2. This will be on the assignment. An alternative to linear probing, or open addressing with linear probing, that can get much less catastrophic results is called separate chaining. And what that means is that you just put a linked list on every entry in the array. That linked list contains all of the items whose keys hash to that index. The linked lists are unordered, so we can always perform the insert process in linear time. And then you could hopefully convince yourself of this just in your head. When you're searching and there's a collision, then the worst case is much less severe in terms of time needed than open addressing. The worst case of open addressing was that we would traverse the entire array and end up at the beginning to find a failed search. Worst case in separate chaining is just that you iterate through all the entries that hash to that index. So in this example, you're looking for an A name that doesn't exist. You would just search through alfors and auden, and then find that Anderson isn't there. This is what our table from earlier would look like using separate chaining. I guess a slightly better picture would have an arrow coming from every index, but I'm sure you could imagine these squares being one element long linked lists. And yeah, like I said, to search for Anderson, you go to index 0 because of the hash map, search it linearly until you find Anderson or reach the end of the list, and then you're done. And it is technically possible for this to degenerate into linear search. And that's if you have the worst hash function in the world, or maybe the worst data in the world, just completely screwing up your excellent choice of hash function. And every single entry of the table is hashed to the same index. Then it goes back to linear search. You just have a linked list and you look through those nodes one by one. But that should be extremely unlikely. Even if an adversary is deliberately messing with you, this actually is a realistic scenario for an attack on some website. Like, if you know that some program that you want to take down uses this strategy and you know their hash function, you could keep sending them web requests that involve things that hash to the same index and then waste a bunch of their time. But Hopefully that doesn't happen to you. Anyway, here's the thing that's not a strategy. You can't just make the table bigger. So say you have 1,000 items to put into your hash table, and you have a good hash function, but you still want to make sure that there's extra space. You want to ensure a low load factor. So maybe you choose an array size of 4,000. Sure. Will that make collisions unlikely? Will it eliminate collisions altogether? In both cases, no. For the specific case of a 4,000 element array, the probability of having no collisions, like your hash function working perfectly, drops below 0.5. So like you have a 50% chance of collisions. When you have 75 elements, you're less than 10% of the way through your 1,000 entries that you wanted to add. The likelihood of a collision happening at all is very high no matter what you do. So you need to have a strategy to handle collisions when they happen. So that's it for hash tables, actually. I think that's going to be it for today because we're going to move on to a totally different topic soon. Binary search trees, which are kind of like linked lists, except you can search through them really quickly. And yeah, that's all. Have a good day, everyone.